Okay, so we begin with the section 5.7, which is complete elastic solutions for a thick-walled cylinder. Complete elastic solution for a thick-walled cylinder. And one of the things which I would want to say right away is that we discuss this section for the sake of solving a variety of interesting problems. Okay. We might skip a few steps of the derivation, especially related to the circular coordinate system, polar coordinate system, cylindrical coordinate system, whatever you would want to call it. But the discussions on the methods will be told sort of briefly. However, it is extremely important as a section to be ignored as such, as a whole. Okay, so that's why we are doing the bare minimum which is required. But you will see lots of questions being solved in tutorial sections and otherwise uh, over this topic. So let's see what this is about, and we'll proceed now. So in this section, we consider a further example of an exact solution within the theory of elasticity for homogeneous isotropic solid. So a homogeneous isotropic solid means, is isotropic part you understand very well. So homogeneous means that it is made up of one kind of a material throughout. Okay, it is not made up of different kinds of materials. For example, if you consider a cement, concrete mixture. So you have the cement and you have these concretes. So the concretes are those hard pebbles which you learn about, and this is clearly not homogeneous in the sense there are these heterogeneities in between, and because of this, the stress strain behavior will be slightly complicated compared to the fact if you had one just cement only. Okay, so this is a heterogeneous. Okay, so we are referring to only a homogeneous isotropic solid, and the problem in this case arises in many engineering applications, so that the solution is in itself of considerable technical importance, and that is one reason which I think we cannot overlook this particular topic. So we have already discussed in one of the earlier classes about this. So if this is the RI and it's a hollow cylinder, so there's a pressure inside where, if you are in a flight, this will be 1 atmosphere, and outside your airplane the pressure will be much less. Okay, similarly if you are in the submarine, the pressure here will be 1 atmosphere for the humans to live, and outside the pressure will be much larger than the atmospheric pressure, depending on how deep you are into the sea or ocean. And especially all those containers which you see on the roads which carry petroleum products from the refineries to the petrol pumps, and then the cylinder which you have in your homes is a thick-walled cylinder. Okay, now the purpose of this section is to solve this problem from the perspective of theory of elasticity. What does it mean? Again, you have the boundary conditions specified. So there are two boundaries of this, one this and the other is this internal boundary. You want to find the stress, strain and displacement at any point of this solid. Okay, that's the, if you can solve this using the theory of elasticity, and that you have to do. So the stress, strain and the displacements must satisfy equations 5.6, 5.7 and 5.8. So that's this thick walled cylinder problem. Okay, now so let's consider a cylinder with inner radius. Let me just rub this off. So consider this thick walled cylinder and it has an inner radius of Ri, the outer radius of Ro, which is shown in this figure. We shall determine the distribution of stress within the cylinder when it is subjected to external loadings indicated in figure 5.18b. So the loadings over here are like this. Please look at this one. The outer wall of the cylinders are experiencing this pressure PO. The inner wall of the cylinders are experiencing a pressure PI. Okay, so this is similar to the experience which I have just shared with you. This can be 1 atmosphere and this can be the atmosphere up in the air or down in the ocean. Okay. Now, other than that, there are loadings of the stress which are sigma naught like this. I mean, the top face of this is also loaded, the bottom face of this is also loaded by a stress which is acting in the direction of axis of this cylinder. Okay, so that is shown by sigma naught. There is a uniform inner pressure Pi, uniform outer pressure P naught, and uniform axial tensile stress sigma naught. Okay, so there are these three loading conditions which are given. Now this configuration provides a model for several practical problems, and we have told you about a couple of them. For example, the cylinder might be a thick walled pressure vessel where important load is the inner pressure, or a submersible hull where the important load is the outer pressure. So that is where this comes up. And eventually, I mean, as I've told you, the purpose is once you find, say, the stress field inside, after that you start using the failure theories which you study in your course in design, and then see whether this homogeneous isotropic solid will be able to sustain the loadings or these pressures. So that is the eventual idea, to use it for designing and design it against failure. So you would be using the failure theories, and if you know those failure theories, you would know that they all depend on sigma 1, sigma 2 and sigma 3, which are essentially the principal stress values, and you would know how to find the principal stress values using Moore's circle or even the other method of eigenvalues. Okay, now if the height h was small, this height h were small compared to the radii, the cylinder will be a plate or a disc. So if h is small, then the cylinder becomes a plate or a disc. And the important load might be the inner pressure which arises from a shrink fit attachment to a shaft. So by this time you should be aware of what a shrink fit attachment is on a shaft. Okay, so for example, if you have this disc, okay, and then there is a shaft like this. So this part has to go into this part to form an assembly, and then there is a shrink fit process which happens. I mean, there are thermal loadings which apply, which allow you to contract and expand, and once it has contracted, you let it go in, and then once it reaches a temperature, it will expand and fit it completely. Okay, so this is a shrink fit mechanism. Again, you should look up a YouTube video to check what shrink fit is. Okay, and in this case it is the inner pressure which the shaft applies on this disc or the plate, which is important. So please have a look at this shrink fit if you are not aware of this by this stage. Okay, so there is definitely a cylindrical symmetry in this problem. I mean, we can easily see that. So we want to define the cylindrical coordinate system for us. So please look at the diagram C. Here you have the origin over there, Okay, any point will have three coordinates like x, y, z in the Cartesian system and r, theta, z in the cylindrical system. So if the point is P, okay, it will have an r component, meaning you move in the radial direction. It will have a theta component, this angular part, and then you have this z height part of it. So that takes you to this point P. Okay, and then if you would want to write the displacement of this particular point, so P has moved to P dash. Okay, so in the Cartesian system, this displacement could have been easily written as, sorry, it should be r theta z. So this displacement could have been written as ui cap plus v j cap plus w k cap. Okay, so that is what u, v and w. So this is the Cartesian, this is the Cartesian, and this is the cylindrical. Okay, now, and because of this geometry, you are forced to sort of come to this symmetry now, cylindrical coordinate system. Like we did in one of the other problems, when we had to use some part of the uh, radial coordinate system. I think it was about three-dimensional moments of force. Okay, so the 15 equations of elasticity in the cylindrical coordinates consists of three equilibrium equations. So you will see a problem 4.4 in which you will again have the 15 equations of elasticity. Okay, it will have three equilibrium equations, six strain displacement relations, and six stress strain relations. Okay, all of them will be in the cylindrical coordinate system. So this problem 4.4 is extremely important. Okay, and you must definitely do this. It will be definitely there in your list, but you must also do this very sincerely, because only with this problem you will get comfortable with the cylindrical coordinate system. Okay, so you have that part very well defined, and the method is exactly the same as you have used uh, in the Cartesian system. So you will take a point, an element. This time the element will have cylindrical coordinates, and then you must apply the force balance and the moment balance. Okay, there's nothing new about that. It's just that that will take slightly more time. One reason you cannot just replace x, y, z with r, theta, z. Okay, you can always say, we already know the hooks, we already know these elasticity relations, 15 relations in x, y, z. Why can't we directly just change, say, replace x by r, y by theta, and z is anyways z? Why can't you do that? One basic reason is that the units are different. See, x, y, and z always have the units of distance, but r has a unit of distance, z has a unit of distance, but theta is an angle. So this causes us to sort of not just directly replace. There's definitely a relation. You know that you can write a point as r cos theta plus r sin theta and so on in the two-dimensional system, but you cannot directly replace them. So because the dimensions to start with are different, so there's no reason. So the equations will not dimensionally match. The left hand side will not dimensionally match the right hand side. So that's the basic reason. But 4.2, 4.3, 4.4, you should be doing all those problems in the tutorials. I think you will be guided along the way that you must do it, and you must have done it by now, by this stage. Okay. So once that is done, we have the 15 equations, and that is given in problem 4.4. So I'm not writing that down. You can please check problem 4.4 and see those equations. 4.4, 4.19. Okay. Okay. Now the Boundary conditions is the next stage which we would want to write, and that is say you want to write the boundary conditions. So sigma r will be equal to minus of pi. Okay, so this is, we are talking about the inner surface, so r is equal to ri. Okay, tau rz is equal to 0, tau r theta is also equal to 0. Similarly, at r equal to ro, sigma r is equal to minus p naught, tau rz is equal to 0, tau r theta is equal to 0. Okay, so that's the second part of it. And when you want to write the boundary conditions, I mean, you can clearly see why there is a negative sign, because the sigma r will actually be pointing outwards. Okay, so, and in both cases the stress is away from this direction. So outside is this one, okay, and inside of it is this one. So you would have minus pi, okay, and minus p naught. Just check the directions over here and see whether this is true. Okay, to the best of my knowledge this is true, but make sure this is one thing which you should always remember, that you should be writing the stress vector as a boundary condition. Okay, not the stress, and that will explain to you why there is a minus sign in both the cases. Okay, so for example, for the outer part, the normal is in line with r, or this direction, but for the inner part of the cylinder, the normal is opposite with the radial direction, and that is why you are doing this. So I sincerely request you to please write the stress vector when you write the boundary condition. So this has been sort of written in a more I mean, some of the steps are missed when we wrote this over here. So you must write the force vector with the normal signs, and then you will see why there's a minus pi and minus p naught in both the cases. So please do that and move ahead only after you have done this part. Okay, so that's the inner and the outer part of the cylinder. Now, if you look at the top and the bottom faces, so what do you have over there? You have z is equal to h and z is equal to 0. Here you will have sigma z is equal to sigma naught, tau rz is equal to tau theta z is equal to 0. So we'll redefine, I mean re-revise the problem for us. The problem is to determine the stresses which, together with the strains and displacements, satisfy the 15 interior equations and the 3 boundary conditions at each point on the boundary surface. Okay. Now the general problem is greatly simplified in the present case because of the radial symmetry of the loading. Okay, so the loading, both the internal and the outer pressure, is radially symmetric, and so is the loadings on the upper and the bottom face of this thick walled cylinder. Okay. Based on this symmetry, we shall look for a solution in which the theta component of the displacement vanishes, meaning the displacement, so this u is in the Cartesian system. Okay, you want to write the same u the same u, okay, not a different u, in the cylindrical system. So then you will have a u r cap plus v theta cap plus w k cap. Okay, so the same vector can be represented in the Cartesian system, the same vector can be represented in the cylindrical coordinate system. Okay, so there you go. Okay, so you want to find this value, okay, because there's a radial symmetry, so you don't have to worry about it a lot. So let's start with this, the theta component of the displacement, and we shall look for a solution in which this becomes equal to 0 and in which all stress strains theta are independent, all stress strains and displacements are independent of theta. So this is happening because of the radial symmetry. So because of the radial symmetry, V is equal to 0, and this V, okay, theta component of displacement will be equal to 0, and all the stress, strains and displacements will be independent of theta. So that's a very important part of it. I mean, the whole point is that if this is your solution, so whatever stress you get at this value along this whole circle, you will get the same stress or strain or displacement. So it will not depend whether on what theta you are, as long as you are on the same r and same z. Okay, that's the first part about this, and the only way to do that is that, I mean, this is what you are looking for, and okay. Now if we find such a solution, we know that the uniqueness principle, that it is indeed the solution. So the uniqueness principle which we have discussed in the previous class, or perhaps before that, is that this entire problem will have only one solution. So through whatever method, if you are able to find any solution like this one, that will be the only solution to that problem. Okay, so you don't have to worry about that there will be more than one solution. That won't be the case. You find any solution and that's the only solution to that problem. Okay, now we also make a hypothesis based on the uniformity of the axial loading that sigma z is equal to sigma naught throughout the interior. Okay, and the stress and strain are independent of, I mean, earlier it was independent of theta only, now we are making it independent of z also. So this is a hypothesis which we have made. Okay, and with these assumptions the problem collapses to a manageable size. Okay, so then after this essentially you have only r to worry about in most places. So you can see the solution in your textbook, and as I've said, there are parts of it which you would find hard, but at the same time the things which I'm telling you to derive, that you should derive. Okay, I've already told that in this class. So once you solve this, eventually you will have sigma r is equal to minus pi r naught by r whole square minus 1 plus p naught r naught by ri whole square minus ro by r whole square divided by ro by ri square minus 1. Similarly, you will have a sigma theta as well. I'm not writing, but that is equation 5.9. The strains in the z direction, axial direction, can also be found. That is equation 5.10. You should check that. So the result part of it is what we'll be focusing on. Okay, so for this problem you have a sigma r and sigma theta of this form. So just to tell you, I mean, if you have this point like this, so sigma r acts like this, sigma theta acts like this. Okay, so at any given r and theta, so you have taken your answer to be independent of theta. That's why you don't see a theta in this expression. Okay, even for sigma theta you don't see a theta. Okay, so that's because you started off by taking it to be independent of uh, theta. Anyways, so these results, which is equation 5.9 and 5.10, will be important, and you will be using them a lot in lots of problems, and they are actually very, very important for any engineer as such. Okay, so let's now see how we can interpret this result. Okay, so consider some special cases. So when the inner and the outer pressures are both equal, like PO is equal to PI is equal to P. In this case, you will find that sigma R is equal to sigma theta is equal to minus P throughout the interior. Okay, it does not matter at what point you are. This will always be true. When the, I mean, this is the case, for example, if you have a empty bottle, okay, an empty bottle is something which you have. So the atmospheric pressure is there inside, the atmospheric pressure is there outside. So the sigma r and sigma theta will be equal to minus p throughout the interior in that case. On the outer pressure is absent, so if, so this is the first case. The second case is that p naught is equal to 0, so the outer pressure is absent. Consider this as a case when, say, you are in a spaceship which has moved outside the atmosphere of the earth. So the atmosphere of the earth roughly extends to maybe around 70 kilometers from the surface of the earth. Please check it, I mean, you should definitely fact check what I tell you. And beyond that distance, say if you are going to Mars, you would have no atmosphere, and hence the inside pressure should be atmospheric pressure for you to survive, but outside pressure P naught will be equal to 0. So that is that case at P naught is equal to 0, and in this case the P naught, all you will have to do is just substitute P naught equal to 0 in all the expressions. So the Pi will result in a compressive stress, and then sigma R will be equal to minus Pi at the inner wall to, okay, to sigma R is equal to 0 to the outer wall. So there's a sprint, I think it's a sigma R. So you have A R equal to 0, but in your textbook it should be, so sigma R is equal to minus Pi at the inner wall to sigma R equal to 0 to the outer wall. So because it has to satisfy the boundary condition. Okay, the tangential stress sigma theta is tensile throughout, with the peak magnitude occurring at the inner wall R is equal to Ri. The manner in which sigma R and sigma theta vary with R is indicated in figure 5.19a. So in this figure, you will see how sigma R and sigma theta vary. So they have been normalized against the internal pressure, which is the only non-zero quantity. Okay, there is no outside pressure as you see over here. So this is how the sigma R and sigma theta will vary, and this distance is also normalized with the internal radius. So all the numbers which you see over here are dimensionless, and this is a very good practice in engineering, so that your so you normalize it away so that all your x and y axis numbers are dimensionless, there is no units. Okay, this is very helpful in analyzing the results, so then you don't have to worry about what the units are and things like that. Okay, So that's the first case, and you see that the from the inner boundary to a place which is two times. So it seems this is the outer boundary. Okay, so it seems it's a 2 times of the radius, and yes, it is given that the outer radius is 2 times of the inner radius in your textbook, and that is why sigma r increases from -1 and goes to 0, and similarly sigma theta decreases from a value over here to a value which is close to say zero point 0.5. Okay, so one of the important things is the sigma theta will not become equal to 0. I mean, that you can see from equations and graph as well. Okay, so figure 5.9 tells you another case. In this case, clearly this is the third case, that pi is equal to 0 and p naught is equal to something, and in this case you have sigma r and sigma theta varying like this. Okay, so this is I mean, these are the cases which are very commonly seen in many engineering problems. So next time you look at any closed object, you should be able to see what are the internal and the pressures acting over there. One of them will definitely be atmosphere if you're seeing them around you. Most probably they at least the outer one. But then what should be the inner pressure? So see a gas cylinder, in anywhere you find things like that, you should be able to see this particular problem. Okay, so this, and then there are some other discussions which follow over here, and I will leave those discussions for you to study. You can take the help of sort of any video or a photo if you don't understand. For example, if you do not understand what a oil hole or a keyway or a notch is when you are studying stress concentration, you should just Google and go to images tab, and then it will show you what a keyway or a notch is. So it is in the last paragraph of this section. Similarly, Saint Venant's principle we have already discussed, I think, enough, that you can solve the problem by taking a simpler boundary condition which is statically equivalent to the original one, and as long as you are away from the boundary, your answers will be approximately correct. Okay, so with this we move to the last topic of this chapter, that is section 5.8, and that is strain energy in an elastic body. So let me just zoom in slightly. Okay. Okay, so in section 2.6, if you go to your section 2.6 in the textbook, let's see. Not 2.6. Yeah, it's not 2.6, it's 2.7. Okay, section 2.7 of your textbook, we had learnt about elastic energy, Castigliano's theorem, complementary energy, potential energy. Okay, that's what we had learnt over there. So we had introduced the concept of elastic energy using springs and uniaxial member. In this section, in this chapter, we want to extend this concept of elastic energy to an arbitrarily linearly elastic bodies which are subjected to small deformations. So you no longer have this one-dimensional springs or one-dimensional uniaxial members. You have this three-dimensional body with all the bells and whistles of stresses, strains in 3 dimensions, and you want to now find what the strain energy is in this body. Okay, so in 2.10, the elastic energy U stored in linear springs. So let me check whether the equation is actually 2.10. Yes, So in equation 2.10, the elastic energy stored in a linear spring is given in three forms. Okay. In terms of the deflection delta, please look at equation 2.10 in your textbook. It is given in terms of delta, it is given in terms of force F, it is given in terms of the deflection delta and the force F. Okay. So we shall find the latter form, U is equal to half into F delta, most convenient for our present analysis. Okay. So the first equality which you see in equation 10 is about delta only, the last one is about F only, and the middle one is about F delta. So we'll use the middle one which has both force and deflection in it. Okay, now because of the linearity, force and deflection grow in proportion during the loading process, and thus the total work done is just one half of product of the final force and final deflection. Okay, so the stress is linearly related to the strain, and because of that, finding the area under the curve is very easy. Okay, you want to now apply the same concept to a small element, infinitesimal element as it says over here, with a linearly elastic solid. So let's look at figure 5.20b. Here you have a uniaxial stress component sigma x, which is acting on the rectangular element. So sigma x is acting, you can see that over there, and clearly correspondingly the sigma x will act over here. Okay. Figure 5.20b. Okay. And I think these symbols are not exactly correct because it's an infinitesimal element. So now the delta x has actually become dx. This has become dy and this has become dz. So I think the z, x and y should not be in the subscript. So please make that correction in your book. Okay, so we are not taking S as delta x delta y because it's an infinitesimal. So delta x tends to 0, that you write as dx. Okay, so in 520b, it shows the corresponding deformation including the elongation due to strain component Ex. So you have to make this correction here as well. In all of these places you should make the correction. Okay. Okay. So 520b tells you about the corresponding deformations in this, and clearly you have sigma x, so you will have epsilon of x, a linear strain, and it will also have, because of this elongation in the x direction, you will also have a contraction in the lateral directions, meaning in the y and z direction, and that is also demonstrated by these dotted lines over here. Okay, now the elastic energy stored in such element is commonly called strain energy. In this case which you are considering, the force, what is the force? The force is sigma x dy dz. Dy dz is the area, so this is the force. Acting on the positive x phase does work on the element as it undergoes an elongation. How much elongation does it undergo? Epsilon x dx. Okay. Now in a linearly elastic material, strain grows in proportion to stress. Remember, sigma x ex. So this is how the strain will go in proportion to x. Thus the strain energy du stored in this element, when the final stress and strain values sigma x and epsilon x are reached. So you see that they will start off from 0, then they will increase, then they will increase. So this sigma x and epsilon x which we are writing over here is the final value which has been reached by slowly increasing these from 0. Okay, and definitely they have this linear variation. So this is equal to half into what is the force? Sigma x dy dz, just from the case of the linear spring which we have discussed, and epsilon x dx. Okay, so this becomes equal to half into sigma x epsilon x dv. So dv is the volume of this infinitely small element. Okay, so that is basically dv is equal to dx dy dz. Okay, so that's the case, and once you want to find the total strain energy contained in this, in a whole body, I mean, you know that this is not your body. I mean, your body is actually quite big. This is your point of interest. Okay, this is the point O, and you have made an infinitely small volume around it. So if you want to find the strain for this entire solid, of which this is a very small part, you must do an integration from 0 to v. Then it would be half of sigma x epsilon x dv. Okay, so that's the first part of it. Now you can, this was for a uniaxial stress. Now if you consider the figure 520c over here, so I'll just remove this, it takes away the focus. Okay, so in this 520, you have this situation of a pure shear. So there is a tau xy acting. First let's check the directions. Okay, it seems to be okay. So this is tau xy acting on the x phase in the y direction, and this is acting on the y phase in the x direction. So technically it should be tau yx, but tau xy and tau yx are same, so it's okay. We'll give it like this. And similarly, the dashed arrows also show the stresses on the other two faces, which we cannot see from this view. Okay. So this is a situation of pure shear. We have already seen that in a two-dimensional case before. Okay, now in this case the force tau x, so that is the stresses, and now you have the corresponding deformation. So because of this you have this deformation. So the dotted dashed line shows the deformed boundary of this. Okay, and this particular value which you find out, okay, is I don't know what is this sigma x doing in this figure. Shouldn't be there. Okay, so I've removed that. I don't see a reason why that sigma x should be there. Okay, so because it's pure shear, you cannot have sigma x in this one. Okay, so with this you have this deformation, and this deflection will be gamma xy into dy. Okay, so theoretically this would be gamma yx, sorry, it would be gamma xy. Okay, that would tell you about the rotation in this particular direction, and the gamma xy dy would be this particular total value because it is in the y direction. Okay, so if you want to now find the strain energy for this small element, okay, so, and the same would happen over here in the sense the tau xy would grow with gamma xy linearly because it is a linear elastic solid. So you would have du is equal to half into, what's the force, tau xy dx into dz. Okay, dx into dz multiplied by gamma xy into dy, and this is equal to half into tau xy gamma xy dv, where dv is equal to dx dy dz. And you would then sort of, if you want to find for the whole solid, you would have to integrate it over the entire volume. Now these are these two individual cases which we have just learned about, and in reality it is unlikely that the solid, or even the part which, the point which is of interest, okay, that will be experiencing only one stress at a time. Okay, it may be the stresses of all types may be acting at that point. Okay, now if all of them are acting, how do you find the uh, strain energy for that small element? That is what we want to address now. Okay, so we consider now a general case of general state of stress. Remember the general state of stress? All those 3 by 3 terms which you have, 9 terms, eventually 6, in which all 6 stress components are present. The corresponding deformation will in general involve all 6 strain components. The individual strain components may depend on more than one stress component. Okay, so if you look at the first 3 equations of 5.2, but we will assume that the dependence is linear. That is an assumption we always take. So if we imagine a gradual loading process in which all stress components maintain the same relative magnitudes as in the final stress state, the strain components will also grow in proportion, maintaining the same relative magnitudes as in the final strain state. So it's just like the whole point is that all of them will deform individually. It's as if the other stresses are not acting, and we have done this before in this chapter. During this process, in which all the stresses and strains are growing, a single stress component such as sigma x will do work only on the deformation due to its corresponding strain, right? So for example, if you have this sigma x, all the strains like sigma x, sigma y, sigma z, sorry, gamma, tau xy, tau xz, tau yz. Okay, so the work done which will contribute to the strain energy by sigma x will only be because of this, which it is this deformation which it is generating. Okay, so that once you do, so strains are going, a single stress component such as sigma x will do work only on the deformation due to its corresponding strain, right? And not the other terms. So it will just be sort of independent of each other. So you see that a normal stress has this sort of a relationship, a shear stress has this sort of a relationship. So if all the components of stress and all the components of strain are acting, this strain energy of the infinitely small element will be sigma x sigma y epsilon y sigma z epsilon z plus tau xy gamma xy plus tau yz gamma yz plus tau zx gamma zx dv. Okay, and you want to find the total value, you would just be integrating this over the whole volume. Okay, so you can do that over the whole volume, 0 to v, 0 to u, and this applies to small strains for linear elastic isotropic solids. And in case you have a plane strain or a plane stress, if you have a plane strain or a plane stress, many of these terms get to 0. There's no stress in the z direction, this becomes equal to 0, this becomes equal to 0. So you will be left out only with 3 terms. Now one of the things, I will tell you about a similar thing which we had done before. For the total strain was equal to this mechanical strain plus the strain due to thermal effects, and we had added, and similarly here you have added the strain energy due to the various forms of stress. This was due to the principle of superposition. because these two were individually small, so you could apply the principle of superposition. On the other hand, this addition which you are doing is not due to principle of superposition, because if you look at this, I mean, if the stress is linearly proportional to the strain, this is actually a quadratic function in strain. Okay, so this will be essentially ex square divided by the constant. So you cannot add quantities which are quadratic. That is not principle of superposition. The reason you are able to act, you are able to apply this concept of adding is the same idea which you have done before. You have a sigma x. Okay, what you do is you start with an undeformed body. Okay, you start with an undeformed body. Right now there is no energy in it, so the strain energy is 0. You gradually increase it from 0 to sigma x first. Okay, 0 to sigma x. See the contribution to due to that, let's call it du1. Then after this, in this deformed state, you please apply from 0 to sigma y, then call that as du2, and then apply, say, the tau x y. Okay, 0 to tau xy, call it du3, and keep it deformed, and then apply the fourth stress, which may be tau yz or sigma z, whichever way you see this. So this is how you are developing this addition is not principle of superposition. It's like doing it one step at a time, and the whole point of this is that the answer will not change in what order you do. In the sense, you can first apply 0 to sigma x, or you can first apply 0 to sigma y, or you can first deform it from 0 to gamma xy, and then apply the other terms. The answer will not change. Okay, the total strain energy will still remain the same no matter in which order you apply these loadings. So that's what you should understand and take away from over here. So this ends chapter 5 for us. The rest of this chapter we will not be discussing in this course. Most probably it will be discussed in your course in machine design, and especially related to the yielding and stress concentrations, and there are concepts of edge dislocation which will come up from again material science. So we stop this over here. If there are parts which are interesting, we find interesting towards the end, we'll come back, but this is the end of chapter 5 for us for this course. In the next class we will begin with chapter 6, which is torsion. Thank you.